All right, the last unit we are going to do in terms of the physics of moving objects is, otherwise known as kinematics, is talking about energy. So we just talked about momentum, and momentum is a conserved quantity. Energy is also a very useful quantity because it's conserved from one scenario to another. So first of all, looking at what energy means can be very difficult to do because energy takes on so many forms, and it's just, in some ways, it's a very generic thing. But energy is just the ability of an object to be able to produce a change. So if something can produce a change, it has energy, and every object has energy in some form. In the right situation, it can produce a change. Again, energy cannot be created or destroyed. This is even more true than the conservation of mass, because mass can actually be created out of energy. So the total amount of energy in the universe really does remain constant. There's no way to change it. Sometimes it's like locked up in kind of like the form of mass, but it's always there. So when we talk about a power company making energy for us to use, or that we're like running out of energy, like that's not true. It's just the power company is taking energy in one form and putting it into a form that's more usable to us. And then once you use it in that form, then it goes into some form that's no longer as useful. And that's, basically how it happens. And so the energy of the universe is basically kind of always going from, for the most part, like a usable form to a form that isn't very useful or as useful. And so some people postulate that someday the universe will suffer what's called heat death, where all the energy has become, this random fluctuation of heat that no longer can be doing anything useful for, anything that would try to inhabit the universe. Okay? But again, that's just one theory. There's other theories out there in terms of what might happen. So we always describe energy as we have a source of energy and it goes to receivers. So the energy is always there, it's just moving. So hopefully we already saw in the lab simulation today is there's different types of energy. So there's kinetic or motion energy. So that's energy that something has because it's moving. And so the formula that we use to describe that is that something's kinetic energy equals 1/2 its mass times its velocity squared. So this is interesting ramifications for like when you're driving, for example. When you are driving, they talk about safe following distances, and really, if your following distance is increasing linearly, so that way you're using like say the 2-second rule or a following distance or whatever. In some ways that's not the best rule, because as you get going faster, the amount of time the distance it takes you to stop increases by the square. So it takes you, if you're going 60 miles an hour, it's going to take you 4 times further to stop in than it will in if you were only going 30 miles per hour. So really you should allow greater and greater distances by the squared. So if you're going twice as fast, you should really have 4 times the following distance, not just twice the following distance, which the 2-second rule would give you. For potential energy, that's energy that you have when you're in a field. So most commonly we look at potential is like when it's stored because of your position. So most commonly we look at gravitational potential energy, which is equal to the object's mass times the strength and gravity of the planet you're on. So that little value g we've seen before in calculations at 9.8 times how high you are. And that height is kind of arbitrary. You can set 0 to be wherever you are. You just have to be consistent in your problem. Where is that 0, and are you above or below it? Okay. Spring energy has to do with, so that x there in the spring energy, that's how far stretched the spring is. So if the spring naturally rests, let's say this is how the spring naturally rests, and now you've stretched out that spring, so now it's further out. How far you stretched it, that's x, and that k there just has to do with the tightness of the spring. So those are forms of stored energy. Either it's stored because of where you are in the gravitational field, you have the potential to move, or stored in that stretched out spring. Then there's thermal energy, and thermal energy is associated with the motion of individual particles. So you may or may not know this, when you warm things up, the molecules move faster. So in some ways, kinetic energy or thermal energy is just kind of a form of kinetic energy, but instead of being on the bulk like the entire object scale, it's looking at like individual particles and how they're vibrating back and forth and moving around. So those are the different types of energy that we're mainly going to be dealing with, is those types. Uh, and then there's chemical energy, which is something that when you're in chemistry you'll deal more with, which is energy that's stored in chemical bonds. But that does come up with ninth grade science when we talk about, like if I start running, where did the energy come from that made me now be able to move? And that is in the stored energy inside bonds inside my body, that stored kinetic, or that stored chemical energy. Some other terms you're going to need to use in class and formulas. So when we talk about work, and again, it can be confusing because we use the term work in our every day-to-day life. Well, like, that was really hard work, or we got to go do our homework, or, I'm going to go work out. Okay? Well, science has work being defined as you're changing energy from one form to another. So when you go to the weight room and you're going to work out, you are doing what scientists would consider work. You're taking energy that's inside your body and you're putting it into a different form, like into the potential energy of the weights, or into thermal energy as you warm up. Okay? So you are taking that, and work is the force in the direction of, so basically in the direction of the motion only. So if it's perpendicular, it doesn't count, it doesn't do work. Okay? Times distance. So basically for work to happen, you have to have a motion, like you have to move the object some distance. So just pushing against the wall, you don't do any work. So the object must move in the direction of the force for work to be done. Okay. Again, just throw this in there. So all types of energy, when we put a number to it, we're going to talk about how many joules, or a J, that we have. And that goes for work too. Another thing that we'll be talking about is power. So power is how fast the work is done. So you might have talked about horsepower, turn engines is oftentimes rated in horsepower. Light bulbs are measured in watts. So those are the most common units of power that you're going to come across. So a bright light bulb has a higher number of watts because it's using, or basically transferring that energy. I guess try to stay away from using, but it's transferring that energy from one form to another more quickly. So it's going from electrical energy to light at a much faster rate. So that's why it has a higher number of watts. Okay. So if you look at LED light bulbs, their wattage is lower because the electrical energy that they're transferring is pretty much all going into light, whereas a regular light bulb, a lot of that energy is going into heat, which doesn't help us see because we can't see in the infrared. Okay, so again, back to the law of conservation of energy. Mathematically, we can say the energy we have before equals the energy we have after. The energy we have before, for this class, when we work through this, and we can put in all the different types of energy, chemical energy and thermal energy into this too, but we're just going to say that we always start with some kinetic energy, some potential energy. We might be putting work in, and then at the end, we're going to have kinetic energy, potential energy, and we might be getting some work out. So some work might be taken out of the system. So how do we actually apply that to a problem? So here's a problem where I have a ball rolling down a ramp, and I want to know how fast it's going. Okay, so again, I'm going to start off, I'm going to draw a picture. So here's my ramp, and it's 1 meter tall, and it's 5 meters long, and I have a 1 kilogram ball, and it's going to roll down the ramp, and I want to know how fast is it going in the end. Okay, and also I should maybe mark off somewhere that there is friction. And the friction is 3 newtons. And that, whoops, not 30, 3 newtons, which acts backwards on the ball. So now I always look at before and after and what's happening to this ball. So you kind of go through, for each situation, before and after, you ask yourself, is it moving? Is it above the ground? And ground can be wherever you want it to be. Okay? So for both before and after, let me ask, is it moving? Is it above the ground? Is there a force pushing it like to go faster? Let's call that a faster force. Is there a force making it go slower? So I'm just going to call that a slower force, kind of a weird terminology. Okay, so before and after. So first, is the ball moving? No. What that means is there's no kinetic energy in the beginning. Is the ball moving after? Yes. So that means there is kinetic energy in the end. Is the ball above the ground at the beginning? Yes. Is it above the ground at the end? No. Is there a force making the ball go faster? And this is actually doesn't really have a before and after. This is kind of more of a, so I'm just going to like shade that out. This is more of a during kind of thing. So is there any force, like a rocket propelling the ball down the ramp? And there is like the force of gravity is making it like go faster, but gravity is already taken care of when I ask if it's above the ground. So there's no force that's making it faster other than gravity. Okay, so I suppose we could make a little note, and I don't think I can get it here, but not gravity. Not gravity. So gravity is already taken care of with our potential energy question. Is there a force making it go slower during the interaction? Yes, there is. Okay, so that's a check mark. So now when I go back and look at, all right, it says because before I have only potential energy, so I'm going to start off with potential energy before, and then I don't have any work being put in, okay, because my force going faster, since this was no, I don't have any work being put in, I don't have any kinetic energy because it's not moving before, okay, so that cancels out that. And then I look at, well, what about what's happening after? After I am moving, so I do have some kinetic energy after. And then after I am having some work taken out because I do have a force that's making me go slower. So I do work out. Now that I've decided here's my situation, I only have potential energy before, and after I have some kinetic energy, and I also have some work being taken out. Okay, then I say that's what I've got. So potential energy, I go back and look at my notes, and potential energy is mass times gravity times height. Okay, kinetic energy is 1/2 the mass times velocity squared. And then the work that's coming out is the force times distance. Okay, now that I've got this laid out, I go back and I put in the things that I know. So I've kind of run out of room here, so let me take and maybe see if I can grab this and make it smaller. Oh, okay, not quite what I meant to do, but that works. All right, so now my mass was 1 kilogram times g is 9.8 meters per second squared times height, I said it was 1 meter off the ground, equals 1/2 mass, again 1 kilogram, times the velocity squared, which I don't know, so I leave it as velocity squared, plus the force, so the force was 3 newtons, times the distance, okay, and the distance was 15, or whoops, our distance was 5 meters. Okay, and actually I found out this is too much. This isn't going to work out. I just realized, shoot. Okay, let's change the force to be just 1 newton. Because 3 won't work. So 1 newton times 5 meters. So over here I've got 9.8 equals 1/2 v squared plus 5. And then I've got, subtract 5 from both sides, so 4.8 equals 1/2 v squared. Then I multiply by 2, so to clear out the half, I get 9.6 equals v squared. And then if I square root both sides, I'm going to get 3 point something equals v. Okay? So that's how we do a calculation. We'll do another one tomorrow when you guys come back. Okay, so you can see how to work this whole thing.